Good morning and good afternoon, and welcome back to the second day of the Nexperia Power Live event, and welcome back to our studio.
My name is Robbie Fernandes, and I'm Global Head of Marketing at Nexperia.
And I'm Petra Beekmans. I'm the Global Head of Communications at Nexperia. We hope you enjoyed the session yesterday on our industrial channel, but let's get started now with our automotive channel.
Here, live with you, are Andy and Norman to share with you a detailed preview of Nexperia's new electrothermal MOSFET models. The session will take about 25 minutes. We will start with presentation and then take your questions. Questions are anonymous, and you can ask your question by using the question pane on the right-hand side of your screen. Please go ahead and ask your questions to our experts or share your own experience and insights. And with that, I'll hand it over to Andy and Norman to begin. Gentlemen, please take it away.
Good afternoon. My name is Norman Stapelberg. I'm a Senior International Product Marketing Manager working for Nexperia's Automotive MOSFET Group based in Manchester, England.
Hi everyone, my name's Andy Berry, also based in Manchester, working closely with Norman, and I support the applications team for automotive power MOSFETs.
Now let's have a look at a traditional MOSFET model. These models typically have 3 pins. Now these MOSFET models give you a good representation of the typical behavior of a MOSFET, but are very poor at compensating for temperature variations. So now let's imagine for a moment we could create a Cauer model that represents the self-heating effect of the MOSFET, and we could shrink that Cauer model and actually put it inside the MOSFET model. This now allows us to have a 4th pin for the MOSFET that actually represents the junction temperature. And it allows us to put a 5th pin there, which is an accurate representation of the case temperature. So this case pin can now be connected to an external Cauer model that represents the PC board or the thermal environment around the PC board to give you an accurate representation of the device in the circuit. So as we all know, when you increase the power dissipation, the junction temperature changes and the MOSFET characteristics change. These new thermally compensated MOSFET models will compensate for any of these variations, now giving you complete thermal interdependency of all the device characteristics. I will now hand over to Andy, who can give you a bit more technical details about these models.
Thank you very much, Norman. So yeah, why do you care about the thermal interdependency and that kind of behavior being described in our models? What I'd like to do is drill down to a few examples. But first off, just start by saying that we're all power electronic engineers, and as a consequence, we also need to be thermal engineers. We need to have a good appreciation of the thermals in our system. And the reason being for that is that you have a PCB and you have many components in your design, and you need to make sure you're operating within their safe operating limits. And quite often, and for a MOSFET specifically, one of those limits is the junction temperature. And for our power MOSFETs, that junction temperature limit is 175 degrees C. So whenever you're doing a design, you need to make sure that whatever powers you are dissipating in your system, you can predict, you can measure and model and ensure that you're staying within those temperature limits. So here we've got a couple of application examples where I'm going to drill down into a bit more detail to what's included in our behavioral model. So here I'm showing motor control and reverse battery protection, and both of those rely heavily on the RDS(on) of the MOSFET. And so as current flows through the MOSFET, you're going to get power losses due to the ohmic losses of this on-state resistance, and the device will heat up. However, as the device heats up, the RDS(on) will change. It's a temperature-dependent parameter. So as your MOSFET heats up, the RDS(on) will increase, and that's going to change the power dissipation in the MOSFET because of the changing RDS(on), and that's going to change your temperature. So now you can start to see that you've got a interdependency of the electrical parameters on the thermal parameters as well. So why it's important to be able to model these parameters is because your MOSFET is going to be dissipating heat, but this is going to impact your system. It's going to have changed the heat flow into your PCB, and therefore you want to be able to model and predict that so you know how much your whole system's going to heat up. So in both of these applications, we can clearly see that being able to model the temperature behavior is key for predicting your performance, and then ensuring that you're staying within the operational limits of your design. Another parameter that we model in our behavioral MOSFET models is the breakdown voltage. And to help illustrate why that's important, I'm going to go into a use case example called short circuit conditions. And this is a case where your MOSFET might be operating a normally resistive load, and for some reason, whether that load goes faulty, becomes short circuit. Now, it could be that the load itself becomes short circuit, or something replaces that load and itself becomes short circuit. Now, this short circuit is suddenly a low ohmic connection to either the battery or the ground, and also has some inductance associated with it. And what happens is if you switch your MOSFET on whilst it's connected to this short circuit, you're going to get a high amount of current very quickly. Now, in most systems, you can design a detection system to switch the MOSFET off when this is detected, i.e. when the current goes too high, switch the MOSFET off. But that's going to happen within a finite period. And therefore, there is always going to be some current buildup, which the MOSFET needs to handle. So the MOSFET needs to be able to handle these high current pulses. But on top of that, due to the inductive nature of the load, there is energy built up into the short circuit, and that also needs to be dissipated into the MOSFET. And this happens typically through avalanches, avalanching the MOSFET. And this is a critical behavior that you want to be able to model and predict to ensure that you're picking a MOSFET that's robust against your short circuit conditions. And taking this one step further, we could apply the same case to much higher power systems where we might be paralleling MOSFETs. So if you had two MOSFETs in parallel, but due to natural production variation, they might have slightly different breakdown voltages. Now, in this instance, you've got one MOSFET with a lower breakdown voltage and one with a higher. As the MOSFETs turn off, the one with the lower breakdown voltage is going to avalanche first. Now, if you don't take into account the temperature dependency of avalanche breakdown in your simulations or your modeling, you're just going to have to assume that first MOSFET that avalanches is going to take all the current. And that limits you to specifying your MOSFET. You have to pick one MOSFET that's able to handle all that energy. However, in reality, and what our models are able to demonstrate, is the fact that the breakdown voltage changes with temperature. So if we go back to that scenario where we've got a slight difference in breakdown voltage, and still the same, this lower breakdown voltage MOSFET will initially take the current first, but because it heats up and because breakdown voltage has a positive temperature coefficient, it will rise its breakdown voltage and it will stabilize, and the other MOSFET will come online and start to share the current. And that allows you to be a lot more efficient in your selection if you're able to take into account the fact that the MOSFETs will share the current in avalanche. So here, accurate behavioral modeling of the avalanche is critical for product selection in your system. Now, the title of this presentation does focus on electromagnetic interference, EMI, and now I'm going to drill down into several key MOSFET parameters that we model in our behavioral models that are critical for EMI. And the crux of the matter is that the sooner you can detect EMI issues, the cheaper and easier it is to mitigate them. You don't want to wait until you've got a physical prototype, that you've done all your designs, you've passed all your testing for normal operation, and then you send it off to an EMC test house to find out then that you're not conforming to one of the standards, at which point it's very difficult to make changes to your design and it's going to be costly. So anything you can do early on in your design that gives you an insight is going to be a very powerful tool, and that's what our behavioral models will offer. And what I'm going to do is drill that down to a few key MOSFET parameters, and one of them is the body diode recovery. So within the MOSFET, there is a body diode, and this is quite often used in half-bridge applications such as motor control or DC-DC. And whenever current flows through the diode, charge accumulates, and this is what we call the diode reverse recovery charge, or QRR. Now, what happens is, When we want to switch to the next switching cycle, we need to remove that QRR from the body diode to be able to turn the diode off and then be able to form a blocking voltage across our diode. And this happens very quickly and can cause some high-speed current transients in your switch node, and that then could potentially lead to some electromagnetic interference down the line in your circuit. So, yeah, for example, these high currents, as well as charge being extracted from the MOSFET, is creating an interaction with your PCB design. So what happens is on your PCB, you're going to have traces which aren't going to be ideal. They're going to have some inductance associated with them. And also within the MOSFET, there's going to be some capacitances. So we're forming an inductive capacitive tank or resonance circuit in our application just from the parasitics. It's unavoidable, but you want to be able to simulate these behaviors to try and predict the EMI behavior. And as I said, trying to get a handle on EMI or EMC as early as possible is key or critical for a successful design. So to add to that, the diode recovery is just one part of modeling the electromagnetic performance of a half-bridge system. We want to be able to accurately represent what happens in both the turn-on and the turn-off transients of your MOSFET in such applications. And therefore, we need good modeling of all the dynamic characteristics. And that really boils down to accurate modeling of the capacitance. And now, because MOSFETs are semiconductor devices, very often the internal capacitances are dependent on voltage. That is, the capacitance will change as the voltage across the terminals of the MOSFET. And that means you have to model this whole behavior across the voltage to get an accurate representation of your MOSFET in the simulation world. So we've talked about a few parameters there, and what we can do is we can lump them all together and start to analyze what our MOSFET and what our circuit is doing from an EMI point of view. And what I'm showing here is the industry standard double pulse test method. It's a half-bridge configuration, which again is common to a lot of applications where power MOSFETs are used, motor drive, DC-DC. And even within motor drive, that covers DC motors and brushless DC motors and permanent magnet synchronous machines. Very common topology. So this double pulse test method really gives you an indication of the performance of the MOSFET in all these applications. Now, how it works is we configure the high side MOSFET Q1 in this example just to be a diode. So we do that by shorting the gate and source together. And the low side is a typical switching MOSFET, to which we apply two on pulses, hence why we call it the double pulse test method. The first pulse turns the MOSFET on, and we have an inductive load that starts to charge up with current. When we turn that MOSFET off, that current will freewheel through that inductive diode, inductor and through the body diode of the high side. And that's where we begin in our application in this test bench, the accumulation of that QRR. The next pulse is probably one of the ones of the most interesting when we turn Q2 back on. And in that situation, what we are trying to do there is commutate the current out of the diode into the low side MOSFET. And that's what's shown there by the waveform. So that's the current through the low side MOSFET. And it goes from 0 to 25 amps as we turn it off. But in that interim period, in that transition, there are some oscillations caused primarily by the recovery charge being pulled out of that high side diode. And that's what causes your overshoot in that current waveform. And then we've got high di by dt, so high rate of change of current with time, causing an interaction with the parasitic elements on your PCB, which causes the voltage oscillations, and then you have a resonance circuit. And you can see that this kind of ringing could potentially cause you problems with EMI down the line. So to be able to model this behavior accurately, you need to be able to capture all the static and all the dynamic characteristics and model the body diode very accurately. And that's exactly what we've done with our behavioral models. We've taken all these parameters and we've tested them on in simulation and compared that against to our bench measurement setup here in Manchester. And if we zoom in a little bit, you can actually see there are two overlaid waveforms on both the current and the voltage. And you can see there's very little difference. And that's due to how well we've modeled all those different parameters. Again, the capacitances, gate drain, gate source, drain source, the diode behavior, and all the other parameters in the MOSFET. Now, what I'd like to do now is to show how you can do this yourselves with our models in a typical simulation environment through this video.
We will now replicate the double pulse measurement in a simulation environment. We are using PartQuest Explore, which is a cloud-based simulation tool developed by Siemens. Here in this schematic, you can recognize the half-bridge configuration, the low-side MOSFET and the high-side MOSFET, the gate signal, the inductive load of 4 microhenry, and the resistance to sense the current. What we can now do is simulating this design and probe the signals that we just looked at in the measurements. Therefore, it will be the high side VDS of this MOSFET and the current through the MOSFET. So we can probe here the high side VDS. Make it a bit bigger. And similarly, we probe the current. And we make it bigger. As we saw in the double pulse measurement, we are interested in the second turn on event, which is this bit. Here we can see the high side VDS waveform oscillating, as in the measurement is something around 36 volts. And here we can see the current waveform. And again, we are looking mainly at the frequency of the oscillation, the damping of the oscillation, and the QRR area. Again, we have a very good match between the measurement and the simulated data. We will now look more closely at numbers and parameters to evaluate what is the error between measurement and simulation.
And this is the same simulation results that were just demonstrated there, showing that close alignment. So I hope you'll agree with me that we've developed a model here that really accurately demonstrates the switching behavior of MOSFETs and will allow you to do early debugging of EMI issues in your system. These models will be available very soon on our website, so please visit us at nexperia.com/MOSFETs. Thank you very much for your time today and for listening. Please share your questions and your insights.
All right. Thank you very much, gentlemen. Great first session of the day. We actually have a couple of questions coming in here. The first one is, how far are these models matched with practical testing?
Yes, so most of the datasheet characteristics are initially represented in our models. Everything from output characteristics to transfer, and then the capacitive characteristics, the RDS on, and then that's across the full temperature range of the MOSFET, so from -55 to 175. Then we take that one step further and we put it in our applications test as well to do a final check, which is what we were demonstrating at the end of that presentation. So that's the double pulse, where it's the interaction of all those parameters together. So it's not one thing you see on the data sheet, but it's the combination of those, the real application performance of our model.
Okay. Thank you for answering that question. The second question that came in first has another thing to say here. These MOSFET models are really interesting. I'm glad they agree. Are these models available for all MOSFETs?
Every single released product that we make will eventually have these advanced behavioral models available.
So I think we can start off by saying that the latest technologies that were released in the last couple of years will be first, so those will all be available and rolled out before the end of the year. And some of the older generations, the previous generations, we will follow up with those earlier next year. The very old technologies we will probably not do, but it will be available for all future platforms as well.
Great, thanks for that addition. Another question here. What was the frequency of the probe DSO used for measurement?
Oh, that's a tough question. Off the top of my head, we tend to use 1 gigahertz probes in our double pulse test system.
Okay.
Just passive probes.
All right. Okay, then another question coming in. What software tools are the models compatible with?
Right. So first one is the part quest, which we showed you in the demonstration. We'll also make models compatible with most SPICE engines, so focusing on LT SPICE, P SPICE, and they'll come in a couple of flavors of languages as well. So not just SPICE, we've got them in hardware description languages as well, which makes them more powerful and faster. So that will be available in Verilog languages, so whatever simulator can take Verilog, and VHDL, which is what the part quest uses as well.
Okay. Great, let me check. We have time for one more question, all right? That's also a compliment to you guys. Thank you for a great presentation. How do you extract the PCB parasitics?
Right, there are several methods to do this, and it's very important for your system to be able to do that. So we've done that for our MOSFET, and when you want to take these MOSFET models to your system, you're going to have to do that for your PCB as well, and it's not an easy task. There are several ways. There's a hands-on way where you start to characterize your components through vector network analyst measurements, or you can start probing the traces. There are a lot of simulation tools out there as well that have EM solvers built in. There are some expensive proprietary ones, but there are some free ones out there as well, which are a bit simpler, but and you can start building polygons. So as I said, that's the two main approaches, either measuring on board with your VNA and then calibrating with simulation in the SPICE environment, or doing it from the front end and taking your layout or your Gerbers and importing it into an EM solver.
All right.
And that brings us to the end of this live session. Thank you to Andy and Norman, who joined us today from the UK, from our Manchester office. And if you want to know more about MOSFETs, you can follow the resource link underneath the screen or chat to one of our power experts. And these models, as Andy already mentioned, will make the life of an engineer much easier, and market-leading tools to support. They're coming later this year, as also Norman mentioned. The team has been working solidly on creating this new tool, and it's already proven successful with one of our major key automotive customers. They're also available as an on-demand video on this website.
So please stay around. Our next live session on how to maintain reliability and performance in automotive using repetitive avalanche MOSFETs will start after a short break.